In this video, we will start to talk about energy. And there are different forms of energy. Here are some examples. Kinetic energy, potential energy, thermal energy, etc. Okay, so depending on the energy scale we're looking at, or depending on the phenomena we're looking at, we can define different kind of energies. Now, our focus today in this video is kinetic energy. So, as the name suggests, kinetic energy is associated with an object's motion. So now first, let's look at one equation that we know from 1D kinematics. It says that if an object starts with some initial velocity, it's called this V naught, and there's this also final velocity, V final, and the object moves along through some process, and it has mass m. And it also pass a cross displacement of delta x. Okay. Now remember, from 1D kinematics we have V final squared minus V naught squared equals 2a delta x. We have that equation. Now let's try to rewrite this equation into some form that we can associate with the concept of energies. First, let's multiply m on both sides. It's m. Okay, and then let's divide it by 2, multiply 1/2 on both sides, and then let's see what we get. Okay, so let's see, the left side, the first term is 1/2 m V final squared minus 1/2 m V naught squared equals. Now on the right side, these two 2's cancel out, so we have ma delta x. Now, according to Newton's second law, net force sigma F or F net equals ma. Okay, so I can replace this F ma by F net times delta x. Okay, and also let's recall the work definition. So work equals F. Let's say for a force F equals F times delta x. And if I look at net force, then it equals F net times delta x. Okay, so now you can see the right side here is work done by a net force. Okay, so after you do a free body diagram for an object, and then you figure out the net force F net, then the work done by such a net force is related to the left side. Okay. Now the definition of kinetic energy is exactly the left side. Its definition is 1/2 mv squared, and we usually have a symbol k to represent kinetic energy of a system. So k equals 1/2 mv squared. So that's these two expressions here. We can write down k final minus k naught equals w f net. Okay, so the change of the kinetic energy of a system equals the net work done on the object. Okay, so that's one of the theorem we're also going to talk about in this video. but that actually inspired us to define such a quantity, 1/2 mv squared, as a form of energy called the kinetic energy of the system. And you can see it actually comes from the 1D kinematics combined with Newton's second law. Okay, so that's the definition of kinetic energy, and let's rewrite this, redefine this kinetic energy. The example here I want to show you is just to inspire us to think about kinematics from the level of energy. So in the future, you will see in a lot of questions, you can solve the same problem with different method. So for example, you can use kinematic equations, and you can use energy conservations. And usually, energy conservation is preferred because you look at the same problem from a different level, from, I would say, a higher level. So it will simplify your calculation. Okay, so now let's talk about the kinetic energy. Now, the definition is the following. So K is the symbol for kinetic energy, equals 1/2 mv squared. Okay, now here's an object. Its mass is m, and right now it's moving with velocity v. Okay, then that is the definition. You can also say it's the v vector dot v vector. So it's like a dot product between the two velocity vectors. Okay, now the dot product gives us a scalar result. So kinetic energy is a scalar, and its SI unit is joules. And let's relate the kinetic energy to the work done on a system. And let's see, so we have from the previous page, let's recall this equation here. So the change of the kinetic energy of a system, right, equals the net work. We call this W net work done on the system. And this network definition is, so here's network. Network definition is net force dot the product, the displacement, ds. Okay. Okay, so now let's see. The net force equals ma. So we can continue with this equation here. So equals ma dot ds. Okay. Now let's also rewrite this a as dv dt. Okay, that's how we define acceleration a dot ds. Okay, and if you look at the ds dt, right, that's our definition of velocity v, right? So let's see. We can continue this equation, mv dv dot dv. Okay, and that will give us a factor 1/2 times m. If I combine this v and the other v, so you get dv squared. So if you think about derivative, if you take a derivative of v squared, you get 2v dv, right? And then you can, of course, you can combine this 1/2 m with v squared. So let's see, we have the whole thing here, 1/2 m v squared, okay, equals delta k. Okay, so delta k, what is delta k? Delta k comes from an integral of dk, right? So let's say you think about some initial moment, let's call this k naught, and a final moment, k final. Now if you integrate this equation, then you get delta k, which is k final minus k naught, like the initial k, and that comes from this integral, right? The definition. So that's why delta k can be written as this integral here. Okay. Now from this relation, right, we know k, if I define it as 1/2 m v squared, then I have all the property that we just talked about. Okay, so I just want to offer you a different way of looking at the kinetic energy definition, and it can be related to the network done on an object. Okay, now let's see the equation that we wrote down here is called the work energy theorem. In some textbook, it's also called work kinetic energy. Theorem. And in the core of this definition is just the Newton's second law, right? Newton's second law, F net equals ma. And then from there, you can rewrite kinematic equations into energy, kinetic energy, and the network. Okay, so let's talk about this equation. Okay, so the delta k equals the network done on a system. Delta k is k final minus k naught equals the right side here is work done by the net force dot ds. Okay, all right, so let's look at the one example here, so that I can show you how to calculate a network. That's our main focus here. How do you calculate network? Because left side is just definition, right? You figure out an object's initial kinetic energy and final energy, and then the key thing is how to calculate right side. What is the work done by a net force? Now here's one example, potential example. Let's say there's a rock and it has mass m, and it has some velocity, let's say v here, and now think about the force acting on this object. So let's say there's a normal force, because it's on a horizontal ground, so experience normal force, experience gravity, and we also want to push it with some pushing force. Let's call it FP, pushing force. And also the ground here is not smooth, it's a rough surface, and it experienced kinetic friction from the ground. Okay, now under all these forces, the object here is moving with a constant speed. So I mentioned the speed of the object, the velocity of the object. Now is a constant velocity. Now from here, let's also say this object moves along this direction, distance of delta x. Okay, delta x. So now let's calculate the net work done by all these forces. Now, since the network, its definition is that it's the summation of all the work done on a system. So we can try to calculate all these work and then sum them up. Then that will give us the network. Okay, so that's one idea. Now let's start from the work done by the normal force. The normal force is perpendicular to delta x. Right? They have 90-degree angle. So when I do n dot product delta x, I get normal force magnitude delta x magnitude cosine 90-degree. So I get 0. The work done by normal force is 0 joule. And the work done by gravity is similar because gravity again has 90-degree angle with the delta x. So it's also 0. Now the work done by the pushing force, let me call it WP, equals pushing force times delta x. Okay, and we know they're in the same direction. The pushing force is in the same direction as delta x, so we should have a 0-degree angle between them. And when I write these P delta x, they're just magnitudes, so this quantity must be positive. Now the work done by Fk equals Fk dot product delta x equals, okay, so Fk magnitude delta x magnitude cosine 180 degrees, and that equals -1. Cosine 180 degrees equals -1, so we get a negative Fk times delta x, and that's negative. Okay. Now if I want to calculate the net work, then I need to sum them up, and I have these two terms summation. Now it turns out these two terms cancel each other exactly. The reason is from the velocity equals a constant, this condition. So since the velocity equals a constant, then Fp plus Fk must be 0, okay, or Fp equals Fk in magnitude. So that would mean the net work equals all the work summation. Is 0. Okay, but we can also think about the net work done by all these forces using the work and the kinetic energy theorem, because delta K equals W net, this equation. Right, so we can say W net equals delta K, which is 1/2 m final velocity squared minus initial velocity squared. Okay, and these two are equal, right? They the same. So we get 0 here. Okay, so I hope that give you this concept of the work definition, and also how you can calculate the total work done on a system, which we call net work. All right, that's all for this video. Thanks for watching.